Hello, and welcome to this presentation. My name is Pawan Khatiwada from Mirza Research Group in the Department of Physics. Our research group focuses on theoretical quantum optics and quantum information. And today I'm going to talk about using strange correlations among quantum particles to understand complicated phases of matter. So let's begin. First, quantum mechanics is the study of quantum particles such as atomic or subatomic particles at the most fundamental level, which we call the quantum mechanical regime. And it is very different than what we see and interact with in our daily lives, which we call classical world. For example, a classical object cannot be at two different places at the same time, but a quantum mechanical particle can and do exist in multiple places at the same time. In fact, they exist as a range of probabilities. And it is only when you measure it, it collapses to one single value for the physical property that we measure. If you thought that was interesting, then entanglement is even more interesting, because if you take two particles that are entangled with each other and measure a physical property of one particle, you instantaneously decide the corresponding physical property of another particle without the need of measurement. And even weirder thing is that the distance between them does not matter. So one particle can be here at Miami and the other can be in the other end of Milky Way galaxy. And you still be able to tell the physical property of that particle just by measuring the particle that you have here if they are entangled. It was this phenomena that Einstein called spooky action at a distance. Einstein actually proposed this idea to show that quantum mechanical view of our world was in fact not complete. And to be fair, entanglement is quite strange, because it is outrageous to think that a particle that is here can impact another particle or interact with another particle that is infinitely far away in no time. And therefore there was a great debate on the existence of entanglement for a long time since it was proposed by Einstein. It was only 30 years later that John Bell developed or theorized a way to test it, and experiments in the following decade proved that entanglement really existed. At the fundamental level of matters, there is strong entanglement between the particles that make up a many-body state, such as electrons in an atom. Strong entanglement generates complexities in the study of such materials at quantum scale. However, we do need an understanding of such many-body states, because it has profound applications in the technologies of the future, one of them being quantum computing. Now, Google has proved that quantum computers can in fact solve some problems faster than classical computers, even the best supercomputers in the world. But it is still a long way from being used for scientific purposes. For that, we need a proper understanding of many-body states and how they interact in the presence of strong entanglement. Similarly, superconductivity is another field in which understanding many-body states can further the understanding. Superconductors are those materials which can conduct electricity without any resistance. And typically, these materials have to be supercooled close to absolute zero. But in the recent past, researchers have found materials that can show this property of superconductivity even in higher temperatures compared to absolute zero. And it is still a mystery for us to understand why they show these properties, because we do not have a good understanding of many-body states yet. Understanding many-body states is one of the biggest problems in physics right now. and it is receiving an increased interest from both government and private institutions because of its potential applications. Now, the problem of many-body physics is very old, and there have been many approaches to solve these problems. But quantum information scientists have found a new outlook to this problem that has been showing a lot of prospects. Uh, and this outlook uses the structure of entanglement in such materials to write complex equations in form of diagrams and simplifies the problem. This is done in the field of tensor network, uh, which has been showing many prospects lately. And tensor networks is not just applied in the field of quantum many-body physics, but also in artificial intelligence, machine learning, quantum gravity, and so on. Even though tensor network is a relatively newer field, it is quite advanced, and there is a knowledge gap between what we graduate level students know and what is expected of us to know to get started on the research on this field. So what we are trying to do is we're trying to develop a review of tensor network theory that can be both accessible to graduate level students and comprehensive as well. After developing the review, we we plan to apply this machinery to solve some many-body problems in quantum information that can have potential application in quantum computing. And so in conclusion, our research dives into the novel field of tensor networks and the problem of many-body physics. After completing the comprehensive review of the theory, we plan to explore its applications in quantum information systems. With that, I'd like to conclude my presentation. Thank you for your attention.